Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today I have a schematic I'm going to share with you. I came up with the schematic for the 20 watt Class A amplifier. Looked like a pretty cool design. I bought it without even knowing what the schematic was. Just looked like, with the heat spreader, big old TO3s, and the heat sinks on the drive transistors, the 5 watt resistors, just a lot of things kind of stood out, the film resistors and so on. So I kind of took a chance. If you've been watching the playlist, the videos in that, me developing this thing and getting it running, it wasn't as straightforward as it should have been. Now really, in the end, I haven't done a lot to it other than reapply the grease correctly or better, in a better way. I added a couple of Zener diodes that are in the schematic that I am going to point out to you. And so let's go look at that schematic. It took me a little while to put together. I did a simulation. It seems to be working. But I want you guys to tell me what you think. Hey, and there's always chances to improve things. So play around with simulation. Let me know what you think. And by the way, if you don't have the MicroCap simulation tool, download it. It's free now. A little over a year ago, the owner of the company retired and decided to give it away for free. It was like a $4,700 program. It's arguably one of the best programs on the market for Spice. So it's not a free one. I mean, it was worth money. People paid money for it, and right up till till the guy decided just, instead of sell the company, just give it away. I guess it did good for him over, I think it was 30 years, something like that. And anyway, great tool, huge library, and I've got a tutorial playlist, and I think I might add this one to it. I probably will, because I'm going to show you a couple things about the tool and how to use it. A couple of things maybe you don't know. I like to do that every time we touch MicroCap, because just, hey, it's the KISS method, right? Just learn a little bit as you go and make it simple. So let's go do that, and you'll see that it works. From what I can tell, it looks like it's working a lot like what I see on the bench. So that's awesome. All right, let me show you the schematic. Okay guys, so here we are. We'd normally come over here and double click there, but I have it open, so I'm just going to open it. And this is the schematic. So when you hit this plus right here, you can make it larger, or minus, or this guy here kind of fills in the screen. All right, so there's the schematic. Now, let me just kind of walk you through it. Over here on the far left, I'm not showing the transformer, the power supply coming in. This is just the stuff that's on this card itself. But I am showing these two things. These are my input DC, my plus minus supplies. And right now up here, I'm showing it's 22 volts, plus minus 22 volts. So it's kind of on the low side. Maybe right now I'll just change that to 25 volts. So VCC is 25. So they're both VCC, and this is a defined statement that says VCC is 25. So, and you can see on this one, the minus sign is tied to this rail. So this is my minus 25, and then my plus rail is tied up here. And so this is my plus 25. Okay. Now, these things here are those power supplies I was talking about, the regulators, and this is that Zener diode. And by the way, I'm not showing the value in here, and this value is a 19.7 volt Zener. I put 22 volt Zeners in there. What I need to do is come up and put the correct Zener in here, okay? But that's easy to do. I just noticed that as I was talking about it. So these are our Zeners for our plus minus regulated supplies. So the way it works is, you get voltage coming in here, right? Our 25 volts comes to the collector of these two transistors. They're Darlington, so we have some good gain here. But so current will come through the resistor here and put a voltage here on the Zener, and the Zener will clamp it there. And then you'll get a diode drop here and another diode drop here. And so we'll have, roughly 20 volts out here. Okay. That's if we use a 22 volt Zener. So that was the part that I changed to get the power up, just to get these rails up, because these rails feed this op amp, and this op amp this is our input signal. So the 3 voltage sources are what I'm supplying to the card. Okay, everything else is on the card. So this op amp here, it's NE5532. You can put up to 22 volts on the rails, plus minus 22. So that was a problem. I wasn't getting enough voltage here because this Zener diode was just too small. It was not getting very much voltage out here. And so now I can do that. Okay, so, and there's lots of capacitors, like these 200 microfarad caps on these op amps. There's a 470 on the output of this regulator. And then there's another 470 just on the regulation of the Zener. So this guy holds super steady with the 1K and 470 mic. And then through here we got another 470, which is, I think that's just almost crazy. Maybe if I was doing it, I would have put something smaller on this capacitor. Instead of a 470, maybe I would have saved some of that capacitance, maybe put these 2 guys that were here 470s, but still, I think they're plenty big. A lot of capacitance out here. The other half of that op amp is right here, and it's on the feedback. And this is, what is actually referred to as servo. It's a servo feedback because it's active. If we have DC voltage out here, look at this. It goes to this 47K resistor and this 0.47 mic cap. Oh, sorry, that's a 470K. And so we have a huge time constant right here. So this guy holds pretty steady to whatever voltage is out here. Say if it's DC, for instance, and it's coming to the plus pin. So it puts out plus voltage. It comes up here into the minus pin of this guy. And so he says, hey, I got plus voltage out here, let's change that. So he puts minus, and this guy tries to drive it back negative. Now, if you have a negative DC out here, then you get negative coming into the plus pin. So this guy goes low. And then when this guy's low, this guy says, oh, hey, let's pump that up. So you got the servo loop here, and it's pretty high gain. So you're able to put, you don't have to have that capacitor on the input. So without the capacitor, you get really good, low frequency response, because you can go all the way out to 20 hertz, 10 hertz, no problem. All right, so going to the right here, if we go way over here to the right, these 2 transistors are the 2 guys on the heatsink, and the 2 down here are the other 2 guys on the heatsink. And then see these 0.22 ohm resistors? These are our 5-watt resistors, those tall white guys, those ceramic resistors. And then we have that air core inductor, and I measured it, it's 1 microhenry. So we got 1 microhenry, and then 4.7 with a 0.1 mic cap is kind of the snubber or the Bouchereau cell. And then I have an 8 ohm speaker. So that I added, and the voltage sources. Okay, so going back here to the drive circuit, we have these 2 transistors right here, Q29 and Q17. None of these reference designators match what's on the board. I did not try to match those up. But these 2 guys here are the ones that are on those heat sinks, those TO220 style transistors that are on those individual heat sinks. Those are the drive transistors. And there's a 1 watt, 150 ohm resistor between them. And this voltage on this guy is what puts the voltage from base to emitter on this guy. See, if you look at the pass through, you got base, come through here, 150 ohm, come back here, and go to the other base. Whoops, didn't mean to click on that. So, yeah, we got base to base, and then emitter back to emitter. So this loop right here, the voltage developed across 150 ohm resistor applies the voltage across these 2 things here. And this is what keeps this guy in class A. So depending on how much voltage we have here, well, that determines how much voltage or how much current we have going through here. And to set that up, we go back between its two bases and this whole conglomeration of stuff right here. It's basically the same thing as a 150 ohm resistor is to this. So now we come back here and we have this transistor, and the way it's set up is you have the potentiometer. It's a 2K ohm potentiometer, and it's between the base emitter. So when the current comes to this 47K, see this big voltage divider? It comes this way through those resistors, through this resistor, through that diode, which is an LED, by the way, and then through this resistor back down here. So you have this path right here. And all these voltage drops add up to, well, depending on how much current you have a voltage drop here and a voltage drop down here on the 24.7Ks, and the rest of the voltage is across this stuff here in the middle, which is essentially the same thing as this 150 ohm resistor is to this setup. So depending on how much we turn on this transistor, if we turn it on fully, there's only 0.2 volts across here basically. So all the voltages drop across these two things, which then there's no voltage between the bases of these transistors, and they're not going to be on. So we want voltage to develop across here. The more we turn this on, the more we turn on the drive transistors. The more we turn on the drive transistors, the more voltage we could get across 150 ohm, and the more we turn on these guys. Okay? Now, one thing that's interesting is this LED, I noticed on both boards, it was shorted out. It had a big solder glob across the two pins. And the two pins are kind of close together, so I thought, when I first saw it on the one board, I thought maybe it was a mistake. But then I saw it was on both boards, and I thought, well, that still could be a mistake. It could be the flow solder machine wasn't set up properly and it just got too much solder. But I think it was done on purpose, and I just, in running these simulations, it seems like it is, because now this guy might have, say, 2 volt drop, right? Well, so the voltage between this base here and this base down here is this LED drop plus this. And I think that took away some of the control you have in controlling the voltage drop across here. So I think the idea was, hey, we can have an LED to show that things are turned on. Not only that, this transistor has a base emitter, and then we have another base emitter right here. These two guys subtract basically from Q29 and Q17, these two emitters. They don't fully subtract because this guy's a higher voltage than a regular diode, so you end up with a little bit more voltage drop, which basically means you're going to guarantee these might, be on a little bit. One of the advantages of doing that is as temperature and current changes, you get the voltage drop across these things changes. And so when you match a PN junction on this side to what's on this side, it kind of they counteract each other. They offset each other, so they balance. And so this LED would balance with, say, Q17. I mean, but since since this is an LED and not diode, it would balance. It still has that PN junction, but it has a little higher voltage, which is good because you want higher voltage over on this side. But yet, you're going to try to control that with this offset, this gain. And I think they shorted that out on purpose because it seems to work really well without it. And when I ran the simulation, I could see that, oh, maybe this guy doesn't help so much. All right, well, anyway, let's move on. So from this drive circuit and all these transistors, the thing that attaches it to the rest of this circuit, the op-amp circuit, is this one connection from output, the feedback back here, and the drive signal from this guy to that. So you have a feedback and a drive path. The drive path goes to the top of this. Now, it basically just needs to go in the center here because you want to take this voltage and pull the voltage between the base here and the base here. You want to go the voltage, higher to drive the signal up, to turn this guy on more, or you want to drive it down to turn this guy on more. So the reason we get clipping on one side more than the other is this circuit, the way this drives. It doesn't drive it, it's not isometric. This drives come to the top side. You can disconnect this in simulation, connect it down here, and you can still drive this up and down, and then you'll see that the other side clips more than the top side. So it's just a matter of just not being quite isometric. Okay, which I think's okay, because we can still get 20 watts. The clipping's beyond the 20 watts, and you don't want to clip at all, so you really don't want to go into clipping. All right, so that's the circuit. Now here, some things about MicroCap. First thing is I have this voltage right here, and right here, VA, this is the voltage I'm changing. So we'll drive that, and I'll show you what that looks like, okay? Now, remember, that's VA. That's, well, here, let me open that again. We are in the sine wave tab. See all the tabs across here? We're in the sine wave. And sine wave, the AC magnitude for AC analysis, okay? And then this is a DC offset, this VO. Then you got phase and frequency. So we're doing 1 kilohertz for now. But the VA is for the amplitude for the sine source for our transient testing. So that's what we want. And up here, I clicked on the show, so it shows up on the schematic. And that's right here highlighted. Okay, so that just kind of shows us DC offset 0, AC is 1. We're not using it, so it's just set up, it was 1 volt, but it doesn't affect our transient simulation. And then the sine wave is from 0 to 500 millivolts, 1 kilohertz, and the phase and all that stuff's 0. Okay, now the other thing I want to show you is like this op amp here. There was not a P version, and so I added the P version, and all I did is I came over here and said new, and I clicked on new, and then it puts all this stuff as default, and then I just looked at the A and I copied it over to this P, except for these voltages. The negative swing, I said it can go up to 19 plus and minus 19. Here's plus 19. And the VE and VCC, I said it can go up to 22. If you go to the A model, you see it's plus minus 15 and plus minus 12.4 for the swing. Okay, and here's the 3 columns we're looking at. You can change out to 1 column if you want, but here's another thing I want to show you. So I click on this so I can show it up on the schematic, okay? The other thing is, if you come to this window and scroll down, you see gate. This one's A, and there's 2 op amps in a package, right? There's an A and a B gate. They just call them gates. It's kind of a holdover from digital circuitry when they kind of borrowed it from that. But anyway, so, digital circuits, often you have more than one device in a package, and usually they're called gates. But, so yeah, over here, if I scroll down, it says gate B. The other thing is I clicked on this box right here, pin numbers, to turn those on. Now, whoever created this part did not put the pin number for this pin 5. You can tell it's pin 5 because it's the only one without a pin number on it. So the power pins are 8 and 4, and yeah, it's just hard to see these, but they're the same pins as these two. They just reproduce them on both gates. So sometimes they don't. In this package they did, and the pin numbers are all showing up here: 1, 2, 3. This one's 7, and and over here we have this pin 6. The only one that's not showing is pin 5, so that's pin 5. So that's how you highlight the pins, how you turn them on, and how you and show the proper pins. You got to call one gate A and one gate B. And I just copied what I saw on the board. Okay. Though now Q10, I want to point out, I'm not sure what that transistor is. I think I have an idea, but I'll get back to you what that transistor is. But for now, I've got this LED shorted just like it is on the board, and it's all hooked up. So let's just come up here, go to analysis, and we're not going to go to that transient. We're going to come down here, probe transient, so we can just freely probe around. Okay, so here's our window, our simulation, and if it doesn't come up that way, you can click on this panel right here. See, if I click on this one, it goes top bottom, but you go side to side, and then that way you can see the windows together. And then I'll just grab this bar down here and scroll over. I could hit this thing up here to resize it, but then it gets real small. So I'm just going to click on here. Let me go up here to vertical, and let's say we're going to click on voltage. All right, now what I wanted to show you is I have a step function turned on. Okay, and what we can do is come up to probe and go to stepping. Now go to this tab right here, tab 2. So there's our V1, our input voltage, and see over here on this pull down window, I have sine VA. So that's what I'm changing on V1. You know, inside that window we had all those parameters, right? We had frequency, all these things, DC value, VO, but we want to do VA. So we're going to step VA, and I was going to step it from, say, 250 millivolts up to 1 volt and 150 millivolts. Now, you know, that's just for fun. Let's change that to 50. Let's get a little more resolution there. And I'll say OK. And then I'll come up here, and if it doesn't just automatically run, I go up and hit that green arrow, and it takes a while. And then look at all these cases. Now, if I hover over the first case, it shows me 250 milliamps and 300. So you see my signal, and then I come up here where I'm clipping, right? So the one just before clipping is 500, and clipping's 550. Okay, and then down here it's 550, and then clipping starts at the next higher one. So it's just like in the actual circuit, the positive clips first. Okay, so 500 millivolts is as high as we want to go. That's just before we clip. Now, if I hover over that, you see how it shows me 16 volts. That's you know, plenty good for 20 watts. All right, and here's something else I want to show you. Now, we're talking about bias current, right? So let's come up here. Whoops. Let's go over here and say current. And let's look at the current through this resistor right here. Now, you see how it comes up and then it flatlines, and then if I look at the current on the bottom half, it takes over and goes up. So I'm getting current, and then it stops, and then current. So, and that's because our pot is set at 2K. What if I step R22? Let's try that. Let's go to step, and I'll go to tab number 1 since it's not being used. And I could do the pull down menu and find R22. I'll go ahead and do it that way this time. Or I could just type it in, and we're going to step the value. And it says from 1K to 4K. So we're going to go from 200, no, let's go from 100 ohms to 2K. And we'll step in 200 ohm increments. Oops, before I say okay, I got to come up here and see step it. I got to say yes. Now I hit OK. Now I'm going to hit this and see what happens. I got to sit here and wait a while because now we're stepping two things at one time. Wow, that's a bunch of crazy stuff. I can't even tell what's going on. So, you know what? Let's come up here and we go to probe and we'll come down here and we could delete curves that we want to, or we could delete all the curves. We'll come up with the table on this and we pick from our table. Let's just delete everything and start over. Okay, now we'll come over here and let's pick the current again. So I think I'm in current mode, aren't I? Go to my probe right up here. Yep, see it shows me I with parentheses, that's current. So let's click on this guy this time. Okay, wow, look at all those. Now, this guy is all the different, bias currents at the different input voltage. And that's 500 millivolts. There's 750. So we got all these different things. It's pretty confusing, right? All right, guys, so what I want to do is I'm going to focus on this set of curves right here, okay? Okay, I'm going to just try to grab this first cluster up here. Okay, there we go. Now ignore this thing right here. Okay, you see this wave right here? This right here, this V8, this is the 250 milliamp. This is when R22 is equal to 100 ohms. You see that? And then up here, there's 300, 350. So this is all 100 ohm stuff. Now when it's 100 ohms, see this wave right here? It's all sinusoidal, this guy right here, and then the rest of these guys clip. This is a little confusing, so you know what I'm going to do? I'm going to go back and I'm going to set this at 500. Oh, it is set at 500. See that? Because that's the maximum we can do with, before we clip, right? Our voltage clipping. So then I'm going to come up here and say transient, and I'm going to stepping, and I'm going to turn off the stepping of the input voltage, this one right here, okay? I'm going to turn that guy off, so I'm going to say no, don't step that one. But I do want to step the other one, so now I'm going to sit here and let it simulate again. Actually, what I'm going to do is I'm going to close this. I just wanted to use that. Now I'm going to go to this probe transient. Now I'm going to let it simulate. Well, and I went through it already, so that was much faster. Okay, now let's click on this resistor. Okay, there we go. Now, look at that, guys. If I go to this top one, that's when R22 is 100 ohms, and the current starts right here. See if I hover there, 2.7 amps. It goes up to 3.3, down to 2 amps. So yeah, that's a pretty high bias current. And if I come all the way down here, that's when we're set at 2K. The next one above is 1.3. I can see right there. Here's one at 1.1. This one just barely clips. That's 900. But look at this one right here. This one, if I go to 700 ohms, I've always got current flowing through that resistor. So that's class A. We're always biased. And if I do that, see, it goes over 1.2 amps, it drops down here. Now, that one or this next one might be better, or even this one. You know, one of these guys. I don't think this one up here on top is a lot of current. If we set right here, we're going to go as high as 1.8 amps and as low as 561 milliamps. So here's the deal. You have to look at the transistor to see where the gain is the flattest. If you let it get almost ready to turn off, like maybe down here, now this is not real close to the line. We still got 170 milliamps, so that might be plenty. That might be just fine. So I would say somewhere around here, we'll have to decide on that as we go. There's a few factors we got to think about, but I just want to show this is how you can look at bias, whether you can tell if it's Class A or Class AB. Okay? If it turns off like these, then you have to, okay, now he's off, the top guy, right? So he doesn't have any current going through him. Now the bottom transistor. So he's handed the baton to the bottom transistor. Now he's pumping current. So that's Class AB. If this guy's constantly providing current, then he's in Class A. And it's just how far in Class A do you want to be to get linear amplification from that transistor. That's kind of the deal, okay? So I think that's enough for this simulation. I hope that was useful. Now just before I stop, I'm going to come up here vertical, go back to voltage, and show you what the voltages look like, just because you're probably wondering. Now look at that. They're all on top of each other, okay? That's all the different cases. That's why it's kind of a fuzzy line. But look, it doesn't matter. I mean, as far as the output voltage goes, one might be noisier. Here, let's zoom in at the top of the waveform and let's just see what we see. Okay, so let's go zoom in on this top right up here. And I hit that window and yeah, look at that. Some of these guys folded over. It got kind of square topped. So let's see what that one is. Okay, that's the 100 ohm. See, that's the one that's biased really heavy. It's really kind of clipping at the top. So there's 2K. Now the next one that's kind of folded over is 1.9. You know, this guy up here might be the optimal one. That's 900 ohms. So yeah, looking at this, it might be 900 ohms is the best case. And 900 ohms, which was, okay, there's 500, 700. This has to be 900 ohms. But this one's kind of not, turning off. So it could be that we're just barely clipping with that 500 millivolts. So you know what? That might not be due to bias. That might just be that we're clipping a little bit too much signal. So let's drop this down to 400 just to make sure we're not clipping. Well, I'll go 450. Okay, just make sure we're not clipping. Now, the wheel's spinning, we changed. Okay, here let's zoom out so we can see what the heck's going on. Okay, there's our waves. Here, let me zoom in on those. All right, so yeah, 900's just barely, just barely running out. It's just barely almost turning off. It looks like it just touches the line maybe. 700, so maybe just between 700 and 900 might be a good place to settle, as long as it's linear gain through there. Okay, let's zoom in on the top again. Look at that. They all look pretty good. So we're just clipping because we're a little bit too high in voltage, but so it's just a matter of, yep, they're all equal. Yeah, so see all these guys, once we get, okay, that's 1.1, and then all the rest of them are just bunched together. So it looks like once we get around 1K and above, they're all very tight. So that's all pretty linear. So I think we're looking pretty good as far as getting that bias current set, right around 1K, 900 ohms maybe. Maybe that 900 ohms might be the right spot. All right, guys, hope that was helpful, and I think it's going to be fun. You can play around with this circuit. You can, what you want to do is save it and then change things and save it under different names so you don't save it under the original name, and then you can mess around with it all you want. You can always go backwards. Remember, Control Z takes you back. All right, that's good for today, I think. All right, guys, so what do you think of that schematic? What do you think of the design? I think I got the schematic pretty complete. Let me know if you think I missed something or if you see improvements we can make, okay? I don't have a lot of time because I'm going to put this in a box, button it up. I'm going to do a couple videos on, I got a circuit I needed to put on the VU meters on the front of that box. Has the cool meters, so I got to get a circuit on that, and we're going to get the power splice settled on. We're going to get the bias current settled on, all that kind of stuff. And, you know, part of that bias current thing is to see if we can run it Class A and not overheat the box. So, you can get a copy of the schematic if you're wondering. You got to be a subscriber. I want to get people subscribing. See a lot of people commenting and asking questions. They're not subscribers, and I'm kind of starting to fall behind. So I'm going to hit the subscribers first. I'm going to try to answer all the questions, but I'm going to hit the subscribers first. Okay. I finally saw how I can do that, and who I can tell who are subscribers or not. So I'm going to answer those guys first. All right, and so if you're a subscriber, send me an email, kissanalog@gmail.com, and I'll send you a schematic, okay? Or I'll give you a link to it or something like that. All right, and let me know what you guys think if you come up with improvements or that kind of thing. So becoming a subscriber is a free way to support the channel. It helps the channel. Thumbs up helps the channel too. That's another free way. You can, join Patreon for as little as $1 a month. I have giveaways, like I'm giving away a meter to one of the Patreons, and I've given away, I don't know, probably half a dozen meters now. Gave away a signal generator. It wasn't a giveaway, it was to a friend of the channel. And anyway, I've got things, more multimeters I'm going to give away. And then there's other ways. Some people wanted to do once a PayPal payment, and so those links are all below, and so are the links to the playlist for MicroCap and also for the Class A amplifier, and and links to my Amazon stuff, which doesn't cost you anything. It helps the channel. So all right, guys, thanks a lot for watching, and thanks to Patreons for helping out, and thanks everybody. We'll catch you next time.